Today's seminar is about a presentation on our product DA202. Our table of contents, this is what we're going to talk about. The challenges for our industry, what the trends are, and what the development is in the coating formulations. And we're going to talk in detail about what the actual role of the wetting agents that we use in these formulations are. And then we're going to compare the performance that we get comparing an APE-based and our APE-free wetting agent. Primarily, we're going to be discussing the benefits of DA202. And then we're going to compare the performance of APE and DA202 in various paint formulations. And you'll be able to see and compare the differences that we get. And then we're going to draw some conclusions from the data that is presented. So starting from the topic number one, the environmental pressures, the push from our consumers to greater sustainability, movement away from petrochemical-based raw materials to more bio-based, and the impact of our raw materials that we use in the industry on our environment, such as climate change. And so the global shift has been to lower and lower the amount of organic solvent in the system to 100% solids, high solids, and then eventually to waterborne or water-based coatings, with using as much as we can of renewable bio-based raw materials and the removal of metals that impact our environment, the aromatics and halogenated solvents that are used in conventional type coatings. And with the regulations such as from the US EPA and the European Community REACH, and then all the various individual countries' requirements either of adoption of let's say one of the world's most strict regulations, or they come up with their own regulations. Each individual country has differences and variations on the limits, the requirements that they would like to see in their paint formulations. And so with this economic pressure from the global economy, typically it's the whole combination of the most challenging regulations that the global companies are formulating for, because realistically you can't have different formulations for every continent, every country that you have business in. So if your product meets the most stringent requirements, it's suitable to sell in every other country. And then in looking at the raw materials, there's a big dynamic in the industry. Many materials are alternatives, substitutes for each other, depending on pricing and supply availability. And so when we look at these individual raw materials, the goal as a paint manufacturer is always to look for something that is an alternative, but in addition to just being alternative, is there an additional benefit that you can gain? So we refer to these as polyfunctional, or provide a polyfunctional coating surface so that the coating itself, in addition to, let's say, being the proper color, because that's the right reason why we paint, to change the color or to improve the appearance of the substrate that we're protecting. And then the second important reason is that because we want to protect that substrate from its environment. So improve the appearance and protection. And so in any raw material, if you can add an additional benefit to what the current material is providing, that's a benefit that the paint manufacturer is looking for. What are the global trends and the challenges in the industry and the development of the response? Well, there's an ongoing ban. In some countries, it's already banned. In other countries, there's upcoming bans and regulations, either on the use or the amount of use of alkyl phenol ethoxylates. And the reason is because of their impact on the environment. It mimics human hormones, so it's a disruptor. It's also bioaccumulable by the biosystem, and then the consequence of climate change on all our formulations. When we change formulations, we have to realize that the evaporation of organic systems was developed by combining and mixing different ratios of different evaporation rates so that we can control the film formation stage of the paint that's applied. Well, when we switch to waterborne, water has a very, very high caloric demand for evaporation, and its evaporation rate is dependent on relative humidity, which is then the impact of temperature and the amount of moisture that's in the air. So the higher the moisture content in the air at a certain temperature, the lower the evaporation rate. So this really impacts then the film formation of these waterborne coatings. And then another global impact that's being accepted as of a benefit to the raw material suppliers and the people and our customers who sell the paint is the increasing acceptance of the tinting color system. It's referred to as the tintometric or the POS colorant, point of sales. This is where, for any chemistry of paint, the paint supplier manufactures 3 different bases: a regular white tint base that's intended to be tinted with 4 ounces of colorant to finish making the paint, or a neutral base that takes either 6 to 8 ounces of colorant, and then the deep base, which is designed to take 12 ounces of colorant. These are all short-filled can bases, and when the sale is made, the consumer selects the color he wants, and then the tint fills the rest of the container to make the 128 ounces that go into a gallon. And the benefits of this is the availability of a whole palette of colors to the customer. And then for the paint store that's selling this inventory and the paint manufacturer, it reduces the inventory of bases that you have to carry in-house. So you don't need to have 1 can of every available color in your inventory. You only need to have enough of the 3 bases and a tinting system to make the color that the customer wants in the quality that he wants. So in our movement to a more environmental formulation, we switched to waterborne coatings and we lowered the VOCs. The shift, again, as I mentioned before, is toward renewable raw materials going away from petrochemical-based, removing or eliminating the heavy metal-based raw materials such as chrome and its effects on our environment, the removal of aromatic solvents because it impacts our air quality, and the halogens because it impacts the ozone system. And then the mineral oil defoamers that have been used traditionally in our architectural paint coatings, they are actually a VOC. Eventually, as when the water's dry, these mineral oils migrate to the most hydrophobic interface, which is the air interface. And there, prior to their evaporation into the environment, they reside there as sticky, oily materials to trap dirt. So it helps, the paint, dry paint gets dirty quicker. And then finally, the ban existing or upcoming on alkyl phenol ethoxylates. So what are the challenges, Kate, that occur when we shift from waterborne to solvent-borne? Well, organic solvents are typically low surface tension materials. They easily wet substrates. So with solvent-based paints, let's just select alkyd-based mineral oil. They're known for their ability to cover substrates, even poorly treated substrates, because of their low surface tension. Because of their low surface tension, they're able to wet contaminated substrates. Now, organic solvents' evaporation rate are independent pretty much of relative humidity, but yes, they are dependent on temperature. So the higher the temperature, the faster the solvent evaporates. So that means when you formulate, you can increase the amount of slower organic solvents when the temperature is higher for the summer season, and then increase the amount of faster evaporating solvents for the winter time. But in water, it's a totally function of temperature and relative humidity, because water has a very high surface tension of 72, which means that on lower surface tension substrates, water has great difficulty wetting these substrates. So in the transition of solvent-based to waterborne system, suddenly wetting the substrate became a troublesome issue with waterborne coatings. And this is where we need to use then specialty additives to lower the surface tension of the water. And we're going to discuss the requirement why, but just keep in mind that in order for a liquid to wet a substrate, the surface tension of that liquid must be equal to or lower than that of the substrate. That's the only way it will spread. If not, it will sit as a droplet on top of the substrate. In the worst case, as a droplet sphere, that would, as an example, a very high surface tension liquid that we're all familiar with is mercury. Mercury in its free form, sitting on, let's say, on a steel substrate, exists pretty much like a ball. It rolls around because it's so high in surface tension. That's why it won't wet that substrate. So if we consider the surface tension of our substrate, most steels and metals are in the 20s, and the plastics go below 20, and some of them go into the high teens. And so that's why, once we learned how to formulate waterborne coatings to wet our metal substrates, when we tried to use them on plastic substrates of lower surface tension, wetting became a problem. Now, if we look at evaporation rate of the water, because water requires so much energy to evaporate, much, much higher than organic solvents. That's why, if you're boiling a pot of water and you watch it, and you know it's hot, but it takes a long time for it to reach its boiling point because water has a very high caloric demand to go from 100 degrees Fahrenheit liquid water to go into water vapor in order for it to evaporate. And its evaporation rate is dependent on the speed of the air moving past it, the temperature, and the amount of moisture that's in the air. So on the evening day of the day, when the temperature is dropping and the humidity is high, the application of waterborne coatings is very, very slow to dry. So if you're unfortunate enough to apply your waterborne paint in the evening, when the humidity is very high, and at night it rains, your paint may not have formed a film that's resistant enough to being washed off by the rain. And then with organic systems, we used industrial quality solvents. With waterborne coatings, the local supply of water is typically what's available, unless the formulation requires pure water, which is distilled or demineralized water, or just potable water that's available for drinking. And all these waters vary in soluble solids content, and the amount of divalent cations have a great impact on the compatibility and stability of the paint formulation. So if we take a look at the components the materials that are used to make a paint formulation. Pigments, well, that's why we paint. We want to change the color. So pigment makes up a big part of the formulation depending on the color that's selected. There are also functional pigments that are put in to add an additional physical benefit to the formulation. Second, binder. We want to protect the substrate. Well, that's what the binder's function is. The binder is selected and designed to cover the substrate, hold these pigment particles as individual particulates while it's protecting the substrate. Third, the liquid solvent, which we use to put the binders into a liquid form. In solvent-borne systems, we take these liquids and we dissolve the resins, which then becomes a liquid paint system. In waterborne, our solvent is water. The binders are not solubilized by the water. They actually exist as individual polymeric particles. So they exist as organic particulates within a waterborne system. And the combination of those three cannot be made into paint unless number 4, the additives, are a part of the formulation. And it's the additives that are a critical part of the formulation, but the selection and the amount of additives used is dependent on the composition and components and the percentages of the pigment, the binder, and the amount of water in the formulation. So it's a fine balance of the specific binder, the pigment, the extenders that are used, and solvent blend that's available and used, because we also have to consider in that liquid phase, in addition to just water, we have some organic co-solvents that help the film formation process. And so the selection of additives to work within that particular combination of raw materials is critical to the success of your formulation. So what is the actual role of a wetting agent? Here we're going to show a little video clip comparing on the left-hand side. This is just water and a hydrophobic pigment, it's phthalo green, organic-based phthalo green. Left side, nothing added to it. On the right side, you can see how rapid that incorporation with just one drop of wetting agent added to that water. What it does is lowers the surface tension of that water from 72 down to the range of 20s, and now it's wet enough to actually displace and wet that hydrophobic pigment particle. So what a wetting agent does is to lower the surface tension of the liquid low enough that it can displace the air layer that's on the particle's surface. And that allows it then to have a very rapid wetting incorporation into the liquid phase. And this is the impact of this surface tension. Different surface tension liquids exhibit different wetting contact angles on a substrate. On the left-hand side, we see 0. That means it's spread out on the liquid. On the right-hand side, we see the extreme case where the contact angle is 180 degrees. It exists as a sphere. On the right-hand side is an example of mercury. And on the left-hand side is an example of a coating that applies to a substrate that exhibits good wetting. So liquids with good low surface energy are good at wetting. And keep in mind that the liquid's surface tension must be equal or lower than the substrate. Here, in a diagram form, we show the air that's around the outside of that liquid, of these pigment particulates. Blue is our water. And on the case is the left-handed cylinder that we saw with the phthalo blue in the air. And that's why it kind of floats up on top. In addition to being lower density, it's got air to make it more buoyant. When we add the wetting agent, it lowers the surface tension of the water. So now it can wet that surface of that green pigment particle. And so it displaces the air and allows good incorporation into the liquid phase. This is the first step of the wetting and dispersion and stabilization stages in wetting and dispersion. Typically, our industry will refer it to as pigment dispersion and stabilization. It's a 3-step process. The first is wetting. What the wetting does, it gives you higher pigment loading, it gives you better milling efficiency, and it gives you better mill base viscosity. So here in a diagram format, what we show is we take our pigment particles, which exist as agglomerates. These particles make contact with each other. Inner spaces are all filled with air, and there's surface air trapped on them. We wet them, then we subject them to shear. This is the dispersion stage. And the reason why we put that energy in is that we want to separate these pigment particles. So we have to overcome the force of attraction of these particles. And so your dispersion force must be greater than the attraction forces holding these pigment particles together. And once you separate those pigment particles, if you shut off your shear and you do nothing else to the system, that deflocculated system will go back in the left-handed direction and flocculate, because the flocculated state is the lower energy state. And so every system is always trying to reach the lower energy state. And the only difference between the pigment that we start with as an agglomerate and the flocculates that we might end up with after dispersion is that the interspaces between these particles, as an agglomerate, they're air. As a flocculate, it's liquid medium. So after we achieve the dispersion, we have to prevent this flocculation. And this is where the dispersion stabilization comes in. When we look at the various mechanisms that we use for stabilization of these dispersed pigment particles to prevent their flocculation. On waterborne systems, we see on the left-hand side, what we do is we put a layer of charged ions on the surface. These are the dispersant molecules that we put into the formulation that have a polar end and a low polarity end. The low polarity end is attracted toward the hydrophobic pigment, and the polar end, which is soluble in water, picks up then a layer of counterions, and so the exterior of these neutral pigment particles, individual suspended pigment particles, all have to carry the same positive charge on the outside. Now, we all know that as charged materials are brought closer and closer together, when they get close enough, there's a repulsion force, like magnets. When you put the same poles together and you bring them close enough, there's a pushing force between them. So when you bring these poles close enough, these particles close enough, these same surface charges set up a repulsion force to prevent actual pigment particle contact. And that's what prevents then flocculation. On the right-hand side, in the case of solvent-borne systems, what we do is we put a polymeric envelope around each one of these individual particles. Now, the requirement in solvent-borne systems has always been that dispersant molecule must be soluble and compatible in the continuous phase. And if it's soluble in the continuous phase, that polymer chain can relax and uncoil and extend out into the liquid medium because it's happy there. So when these two pigment particles come close together, that polymeric envelope around them, those polymer tails bump into each other. And then they prevent then the pigment particles from making physical contact. And be aware of the fact that if you modify the solubility of that liquid medium system, if you modify that so you lose your solubility of that dispersant, that polymer chain will coil up because now it's not happy in the continuous medium. And that reduces the physical spacing between these pigment particles. And there are many cases where you add a diluent, which is a non-solvent, to the paint formulation, or as the paint is drying, where the solvents are evaporating, your good solvent has evaporated more rapidly than, let's say, your diluent solvents. And now you've lost your solubility and you see flocculation. So think about how we in the paint industry test this. Well, that's why we do drawdowns and rub-ups. Okay, we apply the paint, we allow it to dry, and while the paint is still fluid, but if we move it around, it is not fluid enough to recover. So the case of color change indicates that, when we do the rub-up, we've applied shear, we've put energy into the system, and if it changes colors, the pigment that was flocculated will be deflocculated by the shear that we put in. And if the paint is still liquid enough to move around, those pigment particles will reflocculate. So there are many occurrences of laboratories who do, if it's a new operator especially, if you do your color rub-up immediately after application, if the system is still fluid enough and sensitive to flocculation, well, the color change that's observed immediately goes away. So magically, that system has recovered. But if you take that same system and let it allow it to dry a little longer, and then reapply that shear, now you have rub-up that does not recover. So if evidence there, you'll see the color shift. So what makes waterborne so challenging? Well, because of the variability of the chemistries that are used in the various pieces of equipment that are used in the paint industry, the optimization of the stability of the dispersion that we make and the paint's performance is very much dependent on the degree of dispersion. Some paint companies only use high-speed mixers, others use medium mills, and others use high-energy mills. So the amount of energy that you put into the system determines what final color that you can achieve. And then these are very important facts to keep in mind, because this is very much ignored in our industry, is that the stabilization of the pigment during the transition of the paint after it's been applied from waterborne to non-waterborne. That means it's going from polar system to a non-polar system during drying and film formation, because the water is leaving. And when a certain amount of that water leaves, it's no longer a waterborne system. It's no longer a waterborne environment. Now it's an organic environment. And so what if the paint is still fluid enough to flocculate as the stabilization mechanism collapses and falls apart during this film formation process? If it can't prevent that, then you're going to get color change on rub-up. So be aware of that. During that time of film formation, there's a shift from electrostatic stabilization toward steric stabilization. So let's compare then the performance and the behavior of APE versus APE-free wetting agents. If we just look at APE, they're typically nonylphenol ethoxylates. Their biodegradability is only 60%. The rest of it doesn't degrade. I mentioned before, it's bioaccumulates, so the concentration goes higher and higher in aquatic life, in fishes and so forth. And on the structures on the bottom right, you can see that the structure of APE is very similar to the hormone estrogen. So it's estrogen mimicking, and so there are many bans and restrictions in the industry as to how it's used. And this is very challenging because APEs account for 98% of the global manufacturing of the surfactants that were made. Back about 10 years, it was probably 99%, but that percentage is coming down. It's used in everything. And so our industry is driven to move toward APE-free or lower levels of APE emulsion paint. Due to the EPA directive has it effective for till 2019. Canada, reduction by 95% 2010. And in the EU, APEs can't be used at greater than 0.1% after 2003. So depending on where you're located, the pressures on the elimination of APEs is either occurring or it's going to occur.